Good morning, folks. Hope everything is okay with you guys and gals. And I want to welcome you to this is going to be welcoming you to the future, right? Because I'm recording this sometime in the distant past. I can't tell you the exact year, but it would be some. Well, I'll just give some hints. Currently I'm in New York City. I'm recording this at the Archeo Studios. I think there's a mic in front of me with like little springs on it. I'm wearing an old timey hat and apparently maybe some really well fitting polyester, possibly. I don't know though. Everyone's walking around saying this is a long time ago. Anyway, welcome to the future, and also welcome to the last part of chapter 21 for Klein. There's a lot of repetition here, so we went over a lot of mechanisms in class at the first part of this chapter. So we won't be doing a ton more brand new mechanisms. There's a few little cool things that we will go over, but not anything wildly different than what we have already seen. Okay, and so I think we ended off with this slide, right around this slide last time. Okay, so. All right, so now let's just jump right into the prep and reactions of acid chlorides. Okay, great synthetic utility. Acid chlorides are very, very, very reactive. Make sure I have the right pen tool here. Pen pointer options. Such a professional. I'm always ready. All right. Anyway, so an acid chloride can be formed when you treat a carboxylic acid with thionyl chloride right here. And how does that happen? It's a really simple thing. Now, if you know the mechanism for an alcohol with thionyl chloride, then you pretty much know the mechanism for the acid chloride synthesis with a carboxylic acid. Okay, so for example here, this pair of electrons here swings on down. This kicks up and grabs that sulfur right there, which kicks on up that pair of electrons to the oxygen, giving you this intermediate here. All right. Again, imagine that this right here is going to be like your alcoholic part of your moiety, and that's how this looks so similar to what you have here. So remember you have this other thing, right? Remember you have if you had something that looks like this, right? All right, and then you had S. Oh, it's almost a dollar sign. All right. Remember, this is the first part of the attack. Whenever you have a regular plain old alcohol. Wow, this is so filthy messy. All right. It's your first time tuning in. I don't draw this poorly in real life. It's just the pad and okay. Attack's right there, and that goes up like so, giving you this intermediate right here. All right. Redraw that. Redraw that sulfur. Redraw this charge going up like so, and chlorine, chlorine. All right, and what are we forgetting here? The charge. Okay, so you see how this guy here looks sort of tilde, sort of looks like that. That's what we're talking about. All right, and then this guy here will swing on down and kick this off. The same way this is happening here. Okay. So this is how they're almost exactly analogous, except here you have one more electron push, which should be a trivial change to you if you understand the mechanism. All right, so that swings on down, kicks up to chlorine. The chlorine is expelled. All right, and now you have this moiety right there. Okay, so now a chlorine here, which is a conjugate base, pulls off that proton here. Now what you have set up here for is an excellent leaving group. Why is it excellent? Many reasons. First off, you have some nice electronegativity, some nice induction of effects, where you have the electron density being pulled overall in this direction, which is sort of nice, sort of away from this bond, away from these bonds here, which is nice. But very specifically, look at all this resonance that you might be able to have, right? If you were to just kick this guy off here, you have a ton of really wonderful resonance that you can have. You can draw a resonance structure, right? And have another leaving group leave as well. Okay, so you have this leaving group that can leave, and then this leaving group which can leave. Okay, so that's sort of great. Okay, let's see what we have. Let me just clear this real quick. Okay, so you have this guy here is a really excellent leaving group because of some induction effects and also some wonderful resonance that you can draw. Okay, so let's see what happens here. Okay, so the chlorine, which was initially expelled from the thionyl chloride, remember that was on here before. All right, comes in and attacks one more time, and then that happens right there. All right, So this guy attacks in like so. This guy here swings on down, kicks this off, and you have a loss of a leaving group. And now, so here's something that's, here's how the book does it. This is not how I learned it, but I guess it's still sort of valid. But they have the electron coming and swinging down here, and this kicking off, and the pair of electrons parking itself on that oxygen right there. Okay, and that works sort of. And then you have this highly charged this charged species here, which, well, I'm sorry. First off, after it swings on down, you get your thionyl chloride. I'm sorry, your acid chloride that you desire, plus this species here, which then spontaneously breaks down after this pair of electrons swings on down between the sulfur and the oxygen, and kicks off this chlorine to give you SO2 gas here, and then chlorine in solution. And so this is one way to do it. But the one way I always did it, if you want to see a different mechanism, let's see. Let's draw it up here. Let's draw this thing up here if possible. I'll see if I can draw it small and neat enough so you can sort of follow what I'm saying here. There's that chlorine right here. All right. Sulfur, there's that. All right, so here's this. It's a little, again, crazy looking, but please try and follow. Okay, so a pair of electrons here, swings on down, kicks this off, right? And here's how I would normally do it. I would just kick this guy up to here, and then kick this guy off here, and you go directly from there, pretty much there directly to there. Okay. So you don't have to. If you want to draw that intermediate, you can totally do that if you want to. But I mean, it's just so unstable. It's just so reactive. I don't know that I would ever think about doing that. Okay. So anyway, just consider this other mechanism or this one here. They're both right. They're both right. Okay. This mechanism is more favored in the presence of a non-nucleophilic base like pyridine. Okay. Why is that the case? Why is that the case? All right, because remember, right here, you don't have just Cl minus like the book says. You actually have HCl, right? And if you have HCl, that's a pretty strong acid. And what you can have if you have a buildup of HCl, you might go back. I'm going to go back to the original slide here. You might go back here and protonate this guy here. And if you protonate that guy here, and you make this species right here, all of a sudden this becomes less nucleophilic. All right. But if you have pyridine in there, pyridine will help to absorb any excess HCl that you form. All right. So this guy here will not be. It will be. So if you use pyridine, what you'll end up with is this guy here plus this guy here plus not HCl, but you will end up with, right, pyridinium hydrochloride. Pyridinium. Oh wow. I misspelled pyridinium hydrochloride. Pyridinium hydrochloride. This guy here, which is this guy here now, and this guy here, and your final product. Okay. So again, consider using some non-nucleophilic base here. We've used pyridine before. We can use triethylamine is also sort of works, although triethylamine can get a little nucleophilic. And the reason why we use pyridine is because in terms of lab work, this gives the highest yield of your acid chlorides. I've done this personally, and it works out very, very, very well. All right, there's other ways to do it, but this way is a good way to learn how to do it. Okay, so consider using that. Okay. Hydrolysis of acid chlorides, the easiest thing in the entire world. In fact, sometimes it's almost too easy. Okay, what's going to happen here is the exact thing that happens with every other nucleophilic acyl transfer reaction, right? Nucleophilic acyl transfer reaction. We're transferring this guy here to this position right there. All right, same thing, as everything else. Okay, so the nucleophile comes on in, attacks into the carbonyl, tetrahedral intermediate, blah blah blah. This chlorine now kicks on out, and the water here comes back, pulls up a proton there. You make this plus, right? If you're having this guy here leave, right, plus HCl. All right. All right, so again, hydrolysis of acid chlorides is very easy, almost too easy, in fact, that to the fact that you can buy acid chlorides from Aldrich or from some other supplier, but not many of them, because a lot of them, if you give them just a little bit of exposure to the atmosphere that has a lot of water in it, you'll just hydrolyze these to the carboxylic acid, and then you'll lose your functionality. All right, so it's better to make these things in situ, right, which means in the flask essentially. Or in the I actually don't know what situ means, but we use this Latin term for enclosed or in the flask, and it's meant to say you make it in situ and then you react it with something else. So you make the acid chloride somehow, using the ethynyl chloride or whichever reagent that you want to use, and then you react the acid chloride with something that you want to react it with, which is almost never water, right? It's going to be some alcohol or some other purposeful nucleophile. Okay, so you make this in your flask first, and then you react it with something else. All right, that's what in situ is. All right, I'll look up this word in Latin. I don't know what it is. All right. Okay, so often acid chlorides are used to synthesize esters. So here's a way that you would want to be able to use something that is a more purposeful, a more honest to goodness nucleophile, not water. So you take your carboxylic acid, you'd make the acid chloride in situ, all right, and then you'd react it with this 1, 2, 3, 4, 5, this pentanol, right, in pyridine to give you this ester, right. And so this is something that you can do very easily and in very, very, very high yields. This is just one way. This is just one way that you can use an acid chloride to make an ester, right, in a very, very, very high yield. This is alcoholysis, right, and we almost never say this word. We always use hydrolysis because water, we always are very comfortable with saying that water cleaves something, but alcoholysis, all right, whatever. But this just means that the alcohol here cleaves this guy here. All right, it doesn't. That's all it's meant to say. But how I would always refer to it as never as alcoholysis, it would be as like an ester synthesis. So instead of saying the alcohol cleaves this guy here, we're probably doing that on purpose. So I'll say an ester synthesis. This is one of the ester synthesis techniques. Okay, to use. All right. Give the complete mechanism showing the role of pyridine in the mechanism. Well, you know what that's going to do. You know why you need pyridine, right? You need pyridine because you're going to be generating a lot of HCl. And if you generate a lot of HCl, right, that will come back, right, and protonate this guy here, right? If you protonate this guy here will then be positive charge here, but this guy here will be non-nucleophilic. As if you can read that writing. Anyway, so non-nucleophilic. This is crazy talk. All right. So that's why you want to add in pyridine. Okay, the same exact reason why you want to add pyridine to your thionyl chloride reactions and so forth and so on. It just absorbs HCl. All right, that's why you want to do it. Okay. All right, acid chlorides can be used to make lots of different things, like amides here. Okay, here again, the book uses aminolysis. Again, a means to cleave the acid chloride. I always look at it as amide synthesis. I always look at the proactive form of what we're trying to do here, right? So 2 equivalents of ammonia in this guy here will give you a primary amide here. 2 equivalents here, right, will give a primary amide, means an amide with just one carbon thing attached to it. A primary amide, all right? Primary amide, all right? 2 equivalents of RNH2, which is just some alkyl amide, sorry about that, will give you this guy here, all right? 2 equivalents of this secondary amide will give you the tertiary amide right here. So this is a tertiary amide, this is a secondary amide. Why? Because a carbon thing here and a carbon thing here. Tertiary, carbon, carbon, carbon. All right, but you use 2 equivalents of this guy here to attack there, to give you that, and this guy here will attack that to give you that. Now, curiously, why do you use 2 equivalents here? We definitely know this, but let me just tell you why, right? Let me just tell you why. I won't show you because you already know it. You already know this. Why 2 equivalents of NH3 or 2 equivalents of RNH2 or so forth and so on? Look back to your prior slides. Why do you use pyridine here? Why do you use pyridine here? Notice that key heteroatom that is implicated in this mechanism. Notice that. All right, it's the amine, right? It's the amine type. All right. So why use two equivalents of this? Because one equivalent does a nucleophilic addition, and the second equivalent acts as the base to be able to protonate that guy. To deprotonate. To absorb your HCl that you make. Right? The HCl, of course, comes from the HCl from there, the HCl from there, and the H and Cl from there. Notice you have one fewer hydrogen here, one fewer hydrogen here, and one fewer hydrogen here. All these generate HCl, right? And each one, hey, there you go. Each one of them generate HCl, right? And if you continue to have HCl in there, these guys here will become not these guys here, but these guys here will begin to protonate. Okay, so you want to make sure that you do not reprotonate these with your HCl. Okay, so you want to make sure that does not happen. If that happens, and these become non-nucleophilic, let me show you in this case here. If you generate HCl and a ton of it, this guy here can grab some proton there from HCl to generate R N H H H. There. You make that, and of course you make the chlorine. So the HCl salt of this amine here, this guy here has no electrons to be nucleophilic, and this needs to be nucleophilic in order to attack that carbonyl. All right, that's why I need two equivalents. One equivalent to be this guy here, and the other equivalent to absorb the HCl. All right, to absorb the HCl. So you are sacrificing one equivalent of each of these amines to be able to do a complete reaction, which is again totally fine. Because what happens when you sacrifice one mole of these amines right here, they become water soluble. They're water soluble because they're highly polar, right? And you can wash them away in your water workup, and you've done water workups in your lab. So these become very, very, very water soluble. And hey, if you're a poor lab, you can neutralize this solution here and get back your RNH2 to then do some more reactions, okay, if you really want to, so you can recover this. You don't always have to just throw it all away. You can recover this and then go back into this reaction, okay, and do more. All right, so that's kind of cool. All right, and here's again the mechanism, if you want to explain in detail. And here's where the first equivalent comes in. Here's equiv 1. Here is equiv 2, okay? And this guy here is missing a chlorine, so I shall draw it in, okay? All right, where are we here? All right, acid chlorides can also be reduced using LAH, lithium aluminum hydride, okay? When you have an acid chloride, right, you have the ability to add 2 moles of anything very nucleophilic to it, anything that's a strong nucleophile, like a hydride from LAH, or like a Grignard, right, from a Grignard reaction, all right, from a Grignard reagent, okay? So the LAH, just like before, just like when you're reducing an ester, donate a hydride to there, that kicks up, that swings on down, kicks up to chlorine, gives you the aldehyde intermediate, which then you cannot stop at. You can't stop because you have a ton more LAH and or a ton more hydride to be able to use. Although to be fair, LAH only is very useful for a single hydride on the aluminum and possibly even a second. But in my days, I've never seen evidence of them using like every hydride in the LAH. So it's not like you can use, because it's like because there's 4 hydrides on aluminum, I've never seen anybody use 1/4 the amount of LAH that they need. Everyone uses at least stoichiometric amounts of LAH because they're assuming that they only have one really hot hydride. All right. So anyway, so that's why we can't stop here at the aldehyde, and we just have to just go forward. All right. And after this I'm sorry, there's missing one step here. Why is that? Well, okay. Okay. So here's one hydride addition, kicks on up here. Here's a second hydride addition. All right. And then the ultimate protonation event here, where you have either water or acid coming in to be able to protonate this primary alcohol as is. Okay, so there's that. The acid must be added after the LH has given adequate time to react completely. If you throw in this acid, right, early, then this will kill your LAH. All right, your LAH, your hydride would much rather pull off a protonic and an acidic proton than do a nucleophilic addition to here. Again, this is just way too easy to do. So make sure that when you're doing this thing, you want to make sure that you have first you add in your LAH. All right, let's just say one. Let's just say 1 to 2 equivs, equiv, okay, and then 2. After this is all reacted, then you throw in your H plus and H2O or H3O plus right there, okay, and then that just goes. By the way, if you have on your exam or on any assignment, if you were to just write down LAH plus, followed by H3O plus, I'm going to assume that you're going to use excess amounts of LAH to do the entire reaction, because there's no such thing as like, well, I'm going to use the acid chloride and only half an equivalent of this to only get to the aldehyde. No, that's not how we do it here, okay? Not with LAH. With other reagents that we'll learn very, very soon, sure, but right now, absolutely not, okay? All right. Here's where you can use another reagent to go selectively from the acid chloride to the acid anhydride, okay? So if you use something that looks like LAH, but you have something that's bulky in it, right? That makes it very bulky, like OR3, like this is like a tri-trip-butoxy aluminum hydride. It's just like LAH, except really huge and fat. And you only have 1 mole of hydride. You can deliver a single mole of hydride from to here, and then this will give you selectively the aldehyde. Okay, so it'll only deliver one at a time. Okay, so that's kind of cool, right? So how does that stop? Okay, I'm not showing you there, so I'll just give you some little notes here on it. Why does this stop from here to here? Why doesn't you just make the hydride here? I'm sorry, just make the aldehyde here and then have another mole of lithium tri-trip-butoxy aluminum hydride re-add in. Because one of the key intermediates here, after you do the chlorine, after the chlorine leaves here, is that you make this guy here. So this is after you've sort of already done the addition here. So you have this guy here. Well, there's a few different intermediates. One of the intermediates is where the hydride adds in like so and stays like this. Okay, all right. And this is the aluminum salt. Aluminum, and here is O. We'll say R here, and then we'll just draw it out here, okay? Trip-butoxy. All right. This is one intermediate where it just stays like this until you add in water. Okay, this just stays like this. So it's going to sequester this intermediate as is, all right? Nothing's going to react, okay? And then when you add in water, right, one of the theories is that water comes in here, comes in there, attacks that, kicks that off, then gives you this guy here, along with your aluminum oxy, your aluminum OH salt, essentially, right? And this guy here, okay? I won't ask you about the mechanism, but just you have to know that this lithium tri-trip-butoxy delivers a single proton from here to here, giving you your aldehyde. There's one more reagent that we can also use for this as well, which we will go into. All right, and then we'll talk about that in a few minutes. All right, so there's that. Lithium tri-trip-butoxy aluminum hydride. Okay, how are we doing on time? We're doing okay on time. All right. Acid chlorides can be attacked by Grignards. Of course they can, right? If you know the reaction mechanism, and you absolutely do, of esters, ethyl ester with a Grignard, I'll do methyl magnesium bromide. If you know the reaction between this guy here in ether, of course, between this guy here and this guy here, and you know it gives you OH after the first step, this is 1, and the second step here is water. If you know this guy right here, which of course we went over in lavish detail when we first learned about Grignard reagents and their reactivity, then you know this. Chlorine is just a better leaving group than the ethyl alkoxy species here. Okay, so again, first addition here comes in, kicks off chlorine. Second addition gives you again the tertiary alcohol, as you know. So in this case here, the mechanism is exactly the same as the ester reaction of Grignard's with acid chlorides. Okay, so that's exactly the same. Again, a lot of repetition, and it's going to be a lot like that until maybe just a few slides from now. But this is all pretty similar. Here's one of your new best friends. You're going to love this. So what would you say is a drawback to adding Grignards to acid chlorides? What's the drawback to it? The drawback is you can't control the addition unless you really want a tertiary alcohol, which sometimes you want. Unless you want tertiary alcohol, you can't control the stoichiometry of addition to Grignard reagents to acid chlorides. You just can't do that. All right, and so how about if you want to? How about if you just said, all right, listen, I have this R group here. It's an R prime. Right, and I just wanted to say, and I just want to make this guy. I just want to make this guy, but you couldn't, right? Because you have another R group coming in, and again re-adding there, and again making the tertiary alcohol. But what if you want to do this? You can absolutely. All right, using something called the Gilman reagent. The Gilman reagent is another nucleophilic organometallic reagent that reacts readily with acid chlorides. It's a different reactivity than Grignard's. The alkyl group will only add one time to a carbonyl group, which is pretty awesome, right? This is pretty awesome. You take your acid chloride, you take your lithium dialkyl cuprate, and then you add it to your acid chloride, and then you have, look at this, a wonderful asymmetric, if you want it, wonderful asymmetric ketone species. So how great is that? All right, so it's pretty wonderful. Let's figure out how to make these things here. By the way, you won't have to worry about making these guys here. All right, it's just like the Wittig. I'm not going to hold you responsible for the synthesis of them. It's very, very simple. Here it is. You take your RX, your alkyl halide that you want on your Gilman reagent here. Hit it with 2 equivalents of lithium metal here, and then you make your lithium salt. This X here comes from this guy right there, and you make your organolithium. Your organolithium, by the way, is very, very, very similar in terms of reactivity to your Grignard reagent. All right, these organolithiums are very, very, very similar. You've seen this before. You've seen this before in oh, didn't you have let me see, aren't your oh, look at that. Aren't your lithium alkyne nucleophiles, aren't they lithium salts? I think they are, right? So there's that, right? So those are lithium salts. So you've seen this before, right? So they do have a lot of reactivity, a lot of reactive similarity to Grignards. Okay, so you don't want to stop there. You want to keep on going. Okay, you want to take this guy here and treat it with a copper salt, right? A copper salt. And this is why I don't want to really go that far into it, because there's a lot of different things a lot of different moving parts here, okay? So treat it with a copper salt, copper chloride, copper bromide, whichever you want to use, and then you make your lithium organocuprate, your lithium dialkyl cuprate. This guy here adds 2 times, because using half an equivalent of copper, and it adds 2 times to give you this lithium dialkyl cuprate. You can do, and you have a lot of different choice here. You can make you can make phenyl, lithium diphenyl cuprates. That's a very popular thing to make. All right, so there's that. And this is how you just draw it out. You draw it out this way here, and then CULI. Here's the type of thing. So here's the form this written thing takes. You take your R group, whatever the R group is, put it in some parentheses. Put the 2 after the parentheses there, and then CULI. All right, that's the form that you draw this reagent in. Okay, you can use phenols, you can use many alkyl groups, as long as they have some reactivity to be able to make this, and then to be able to make this guy to then react with this guy here. All right, but you have a lot of versatility there, so it's a very cool thing. All right, so again, consider using Gilman reagents to add to acid chlorides to give you symmetrical or asymmetric ketones. All right, very cool stuff. All right, prep and reactions of various acid chlorides. You have a ton of. It was this nice pinwheel here, which I really believe you should not just digest thoroughly, but also make sure you know the mechanisms for all these things here. But you know what? You know pretty much all of them. All right. If you know one, you know most of them here. Okay. So here's your Gilmans, which we just learned. Here's your Grignards, which are dissimilar to the Gilmans, but they share a commonality where they're both organometallic reagents. All right. Lithium, aluminum, LAH, and lithium trialkoxy hydrides will give you this guy here, which this again is still technically an organic and metallic reagent because you're using metals here and organic species. Okay, and your LAH, which again is which is essentially, like I said before, like the hydride version of a Grignard. You really can't control it. You really can't control how many equivalents of LAH that you can add. The same way you can't control how many equivalents of Grignard you can add. Okay, and then from here all the way up here is essentially the same mechanism. Okay, just changing the nucleophiles. Okay, from here to here, thionyl chloride, or you can use PBr3 if you want the acid bromide. That works out too. I've done that. And from there back to here, water and pyridine, or hell, just water. Believe it or not, right? We'll just give you. We'll give you go from here to here, right? We'll do the acid chloride hydrolysis procedure. Fill in the necessary reagents for the reactions below. All right. I won't fill in the reagents for you. You should do it for homework and make sure that you're very happy with it. But I will drag you through it, and I'll give you some hints along the way. I'll even say, give you some of the, push you in the right direction. All right, from here to here, this is a carboxylic acid. This is a carboxylic acid chloride. How do you make the acid chloride from the acid? You know that, thionyl chloride. From here to here, right? From here to here, how would you add? So you have this acid chloride right here, and remember, this carbonyl here is this carbonyl right here. All right. So what do you have to add? You have to add in this guy here. Wait a minute, you're forming a carbon-carbon bond with this guy here. Can you use a Grignard version of this? Can you use that? Will that work? Well, hell, that will add, right? That will add. All right. MgBr plus. It will add, but it'll add exhaustively, and it'll add once, and then it'll add a second time. So you don't want to use a Grignard, right? So consider using a Gilman. All right, Gilman. All right, reagents. Cool, huh? Well, from here to here, what do you want to add? You guys are not making a carbon-carbon bond a carbon-carbon bond. You're making a carbon-nitrogen bond, okay? So imagine this is just an acid chloride, treating it with this appropriate amine. How many equivalents of the amine do you want to use, though, is the question. A few slides ago, there was the answer. All right, so how many equivalents? So you want to use this amine, of course, but how many equivalents? All right, please look back to the prior slides, or if you want to wait for the answer is 2. All right, because you know that, right? With the first addition is going to be the nucleophilic addition. Then the second use of this amine will be to absorb the HCl, right, that is liberated from this reaction, okay? So make sure that, again, you're comfortable with all those mechanisms. You don't have to know the by the way, let me just let you off the hook. There's no mechanism that you have to know here, okay? From here to here, the mechanism is still sort of not debatable, but it's not part of this course. Don't worry about it, okay? This is not like a Grignard reaction, okay? So don't worry about that. All right, just from here to here, just know this transformation, but don't worry about the no mech, okay? Just know the synthesis of it. Just know this, okay? And that's going to be important, okay? You have a lot of stuff in your toolbox at this point, okay? We know that. We know that. Preparation and reactions of acid anhydrides, okay? Acetic anhydride, right? Can be synthesized by heating 2 moles of acetic acid. I want to point something out to you. First off, this crazy heat. All right, the fact that this is called an anhydride, all right? And we talked about this before in class a little bit, but anhydride just means without water, right? And it means without water. So this guy here, it's hard to see that this has the equivalent of water in it, because it doesn't. It just only has one portion of it, right? But this guy here is the part where you'd say this has lost the elements of water. Let me draw the immediate precursor to what this is. So this guy here comes from, right here, this guy here comes from 2 moles. I'll try and draw it in some sort of obvious way for you. All right, this is 2 moles of acetic acid, heated the bejesus out of it to make the acetic anhydride, right? And so what you have lost the elements of water, making it the anhydride. So you have lost this and this right there. So H2O. H2O. That's where that is the elements of water that are lost, and this guy here is stuck onto here, giving you this guy right there. Okay. So why is so much heat needed to drive the equilibrium forward? Well, you're making an overall stabilized species, but these guys here are not very nucleophilic, right? Not really. All right. And also you are losing some of this resonance here to have it react as a nucleophile to form this guy here. This process doesn't work for most other acids because other structures cannot withstand such high temperatures. So stick to acetic anhydride if you want to make. I'm sorry. Stick to acetic acid if you want to make acetic anhydride. Don't do anything else. Like don't try and do other some other crazy more elaborate carboxylic acid to make the anhydride if you have like stereocenters in it and stuff. Just stick to this one here essentially to make this. Okay, because there's other ways to make anhydrides. Let's go over the mechanismo of this. All right, pretty straightforward stuff, really. All right, and we can think of it this way. And this is just one mechanism. There's other variations on this mechanism, but this is overall going to be consistent with what we're learning, and so. I'll stick with something that looks consistent with what is in the book. All right, this guy here will essentially attack here, giving you this guy here. All right, now you know my preference would be to would be to protonate this guy here with that proton here and then have that attack. But again, why would you generate a high energy intermediate when spontaneously? Why don't you just do the attack first and then worry about what happens after that? So that's sort of why we're doing it, right? This is a choice. But overall, if you really want to protonate this guy here with that acid, especially at this temperature, absolutely you could. Absolutely you could. All right, that's just your choice if you want to. All right. So this guy here is like so. Here's your hydrogen there. There's your comically long oxygen-hydrogen bond right here. Here's your new bond that is formed. This is OH right here. And there is that guy right there. Okay, and let's not forget this. All right. Now, again, normally I'd say do a proton transfer from here to here, and then just get this all nice and equilibrated, and then break down the stuff, and then have this guy kick off. But one way is no right or wronger than the other way, except to say wronger. That's pretty wrong to say. So anyway, but here's what I will do. I will draw this out. Proton shift, proton transfer, whichever you want to say. With that guy here, and this guy here goes from here to here. Why? Making it a good leaving group. Let me make this a good. Oopsie, made a mistake. Scratch that out. O minus. OH2 plus there. This guy here swings on down, kicks that puppy off there, and then there you are. Then you have your water that is now liberated, and you have your acetic anhydride, which you've just made. Okay. Don't get me wrong, though. I mean, it's easy to hydrolyze acetic anhydride. If you take acetic anhydride and you leave it open to the atmosphere, especially in with very humid weather, or even not so humid weather, just normal like summertime weather, it will hydrolyze. This is not so hardy that it won't hydrolyze. In fact, you always want to use, if you want to use acetic anhydride in a synthesis, you want to make sure that you use a new or a fresh bottle if it's possible, because this guy here will absorb some water and then again go backwards, and not with 800 degrees. Trust me, it's forcing going from here to here. It's forcing that way, but not forcing going from here to here. You can use hell at room temperature or below. We'll go from here to here. All right. Why? These are very, very, very. Why can't I draw? Okay. These guys here are extremely electrophilic carbons, okay? Very, very electrophilic, okay? So, again, be very careful with that. Again, and also, if you're doing this in real life in a lab, always come by my office to chat with me if you want to talk about, you know, some hints and tips on how to use acetic anhydride. But anyway, but yeah, try and use this as a fresh jar as possible of this stuff if you want to. And almost no one generates it, you know, in lab before they use it. It's just too crazy, and this stuff is cheap enough that you can just buy it. All right, so a more practical synthesis occurs of acid chlorides when you want. So okay, so what's the primary draw? So there's two drawbacks here, right? One drawback is that it's crazy hot to make this guy here. Okay, so that's a major drawback. You have to use a crazy amount of heat to go from here to here, and that's not good at all, because it also limits, you know, how sophisticated your carboxylic acid can be. All right, so you won't do that. You won't generate. So you can't use anything that is very delicate over here. Okay, firstly. Secondly, notice you can only make symmetrical anhydrides because you just take essentially a flask of this or a vessel of this at 800 degrees under pressure to make this guy here. This guy here are symmetrical halves to this anhydride. And so, but let's say you wanted like one half being ethyl and one half being like phenyl. You can't do it this way. You just can't throw in this guy here plus benzoic acid and then make the acetic benzyl anhydride, right? The acetic phenyl anhydride. That doesn't happen that way. So consider making, you know, using an acid chloride and then some carboxylate, right? Which we can easily make. How do you make a carboxylate? We know that. Take your R group, whatever the R group is. Could be phenyl. It could be alkyl that you have there. And then look at that. You just take your favorite base. I mean, you know, we always use hydroxide for everything, but consider using sodium bicarb, NaHCO3. Why do I love this so much? Is because it's a non-nucleophilic base, which once you pull the proton off of it, this guy here just bubbles away, and you make water and CO2 gas. All right, so once this guy here pulls off this proton here, you end up making carbonic acid, H2CO3, which then spontaneously breaks down to water and CO2 bubbles. All right, so, and there's nothing here that's very nucleophilic that will get involved with any of your reactions here. But here, if you don't use up all the hydroxide and there's some hydroxide laying around, what do you think that hydroxide is going to do to that acetic acid chloride? Not wonderful things, right? But if you want to make the carboxylate that way, sure, use your sodium hydroxide or your potassium hydroxide or hell, whatever hydroxide you want to use. All right, and then make your carboxylate that you'd like. All right, whichever one you want to use. All right, whichever one you want to use. Take another sip of coffee, why don't you, Chris? All right, hold on. That's some good stuff. Okay. So your sodium carboxylate salt here. Okay, this guy here will attack into that carbonyl right there. Again, tetrahedral, blah blah blah. You've seen this 1,000 times already. Kicks on down and makes this guy here. But this, again, your graphic in your book doesn't show you the wonderfulness of this, right? Imagine R is prime, and this guy here is not prime. Okay, so this guy here will attack there, and you can actually make asymmetric anhydrides, right? Where this is R and this is R prime. All right, it's really, really, really wonderful. All right, and by the way, you don't even have to. Okay, and also you don't even have to worry about making asymmetric anhydrides. You can make symmetrical ones. So you can make this if you want to. Just have that guy there. You know, treat this guy here with base, make the carboxylate, and then treat this guy here with this acetyl chloride. Okay, crazy stuff. It's pretty dangerous. Be very careful, right? It'll make you cry, and if you breathe it in, it's a bad thing to breathe in. All right. But imagine if you made this species right here, right? You know, have this set up. We treat this guy here with NaOH. Wow, this is so crazy. All right, thank you, backup complete. All right, O minus right there. All right, imagine this guy here. Oh, it's the pad, it's not me, it's the pad. Cut it out. All right, there's that. All right, and then synthetic mechanistic step here will give you this guy right there. Okay? Pretty cool stuff, right? So you don't need to do this way if you don't want to. You can just do it all this way right here if you want to do the carboxylate acid chloride technique, which I would recommend, right? Again, as organic chemists, we are control freaks, and we want to have things done our way. You know, we don't want to make it too hot or too cold. We want to have it done, in a way that we can control it. Okay. Given that they both contain good quality leaving groups, how do you think the reactions of anhydrides compare to the reactions that we've already saw for chlorides? Okay, this guy here is a leaving group. This guy here is a leaving group. Which has a better leaving group, and why? Which do you think? Which one? Well, we know we sort of already saw the answer, right? We know what it is. We know that chlorine is going to be the hottest group here, and this is pretty hot, right? Because again, chlorine is a good leaving group because it's a very stable. It has a very stable anion, and that's why that is. And then this guy here is also a very good leaving group. Why? Mostly because of the resonance that occurs after the bond transformation happens. Okay, so after you attack something in here, this guy here kicks off. This guy here can do this, and then go on and do some resonance there. All right, and that's why that's so stable. So you make Cl minus here for a resonance for a stabilized species there, and for here you make another resonant species. You make a resonant species here, which again is very stable. Okay. All right. Again. So for acetic anhydrides, the reactivity again is very similar, and look at the same exact pinwheel here. The only thing that's really different here is this preparation right here, which we sort of just went over. All right, this going forward from here to here. But again, this is all the same. Okay, all the same stuff. All right. So acetic anhydride is used to acetylate an amine or an alcohol. So this is a way to protect. It's another protecting group, right? So we know we have a lot of protection knowledge now. We can do tosyl chlorides. We can do TMS chlorides. We can do acetals as protecting groups for hey, what am I doing here? Right? We can do acetal. Or we can make the acetals, right? Right. If we want to do that, or again use just use several equivalents of an alcohol, right? And so this is one example, and another example, right, of another protection group here. What do we want to protect? What are we protecting so much? We're protecting the fact that we don't maybe not want to deprotonate this inadvertently, so we'll put this on. So you say, well, great, yeah, wonderful, but then how do you go back from here to here? Oh, we know that. We know how to do that, right? How do we go from here to here? NaOH, sodium hydroxide. We'll hydrolyze this ester from here to there, right? And that does it very very readily. Here to here, if we want to protect one of these protons or both these protons, we can put one acetyl group here or two acetyl groups here as well. They both exist. You can both make them. And now the process of cleaving that is a little bit, you can do it with hydroxide, but it's not as readily done. It's just, these amides are extremely stable. So you can do it, but you have to use forcing conditions. So this is not the best way, in my opinion, at this point, to protect a primary amine this way. Okay, preparation and reactions of acid anhydrides. This guy here will attack this hydroxybenzoic acid here to make aspirin. Okay, and then if you want to make Tylenol, you can take this aminophenol here to make Tylenol. And this guy here will attack this phenol right here, and this guy here will attack this amine right there. Why will these guys here attack that phenol and then that amine? Anybody know? Why do you think? Okay, these guys here are more nucleophilic. Here to here, and then this guy here is also more nucleophilic from here to here. Okay, from here to here, all right. We have this is a semi decent nucleophile, but remember these pair of electrons here are non-localized. These are delocalized. So it's like this is a charge that's spread out over 2 atoms or 3 atoms here. Okay, so that's why this won't attack here readily, but this guy here will attack. Well, this guy here has a lot less resonance to it, and this will attack into one of those guys here. So this guy here is the more nucleophilic out of the two. Now, so why does this not attack? Why does this attack this nitrogen here and not this oxygen here? Does it not go in line, right? B, C, N, HOF. Isn't oxygen more electronegative than nitrogen? So why isn't the oxygen being acetylated? It is being acetylated. It is being acetylated, but maybe nitrogen reacts a little bit faster. All right, maybe that reacts a little bit faster. All right, so that might happen, but don't get me wrong. You cannot. This reaction here from here to here is not a clean reaction. You do not just make this guy here. You make both acetylene groups there. But how do you get to this? So if I was going to make Tylenol, here's what I would do, honestly. I would take this guy here, throw in acetic anhydride, and I wouldn't get this guy here. I'd get the both acetylated species here. I'd get the amide here and the ester here. I treat this guy here with sodium hydroxide, probably at 30 degrees, and this would selectively hydrolyze this guy here before it hydrolyzes this. Okay, so from here to here, this is not a clean reaction. I don't care what the book says. In real life, it does not happen as cleanly as this. This I do believe, because you need some energy to be able to acetylate that acid here. But from here to here, it's not as clean as this. All right, so you have to do something else. You have to do something else. Okay, and again, the reactivity says that the OH should be more reactive than that. And again, nitrogen might be more reactive for various reasons, but again, they both react. So don't. But this here does not happen. This happens. Okay, and I'll just clear this out real quick. This guy here is the predominant thing that's made, especially if you have like one equivalent. All right. We'll just do this, and here's what you can do for like shorthand. If you want to, you can draw draw that out, or you can just draw A lowercase c. A lowercase c. So this is the diacetyl group. This is what happens. This happens, I'm sure, but this happens here more so. Okay, so you have this guy here. You have some of this where this is the only thing that's acetylated, and then you have this guy here. So you probably have, my guess, three products. Okay. But this guy here would be the one that I would expect you to get if I were to give you this on the exam. Okay, so please make a note of that. All right, in your class notes that you downloaded. Okay. How are we doing on time again? We're doing all right. All right. Here's a really cool reaction called the Fischer esterification, and the Fischer esterification is the cheapest and probably the cheapest way to make esters from carboxylic acids, and I love this. It's just so great, okay? And I can show you a really easy way. Again, if you're working in a lab and you want some hints and tips on how to make these esters, I have a ton of experience here for you. So you can always come and ask me if I'm still alive. All right. So here is your. Let me see here. So here is your carboxylic acid. And this guy here is a protonated methanol. This looks weird, right? The real write-up for this is, and I'm sure you can see this in your book. Let's just say we're making this guy here. So you're gonna take propionic ester here, and you want to make the methyl. So you want to make you take propionic acid and you want to make the methyl ester. Okay. You want to make this guy here, OMe. Okay. What's your reaction setup look like? It's going to look like your methanol. Whatever alcohol you use is going to be the other part of your ester, and you want to use some HCl. And here's what I use. Right, I use anhydrous HCl. What's anhydrous HCl? Anhydrous HCl is HCl in gaseous form. You take your propionic. You take whatever your carboxylic. You take whatever whatever acid you have, and you suspend it or you stir it up in whatever alcohol you want to have be the ester. All right. So here I would take propionic acid and spin it around in a flask of methanol, and I would take my lecture bottle of HCl gas with a little pipette on the end of it, and I'd bubble HCl into this flask right here, and then after roughly about 15 minutes, the reaction flask gets hot, and then you make pretty much qualitatively this guy here, right? And then depending on how big your carboxylic acid is, how big your ester is here, you can do an extraction, or you can just do an evaporation and just evaporate off your alcohol if you wanted to. So you can do an evaporation or an extraction. It really goes like a shot, okay? But here's how the book writes it up, because the book is a little bit weird though, but okay, I can see why he would say it this way, but it's not a good way to think about the real reaction, okay? But So you can have this guy here protonated from your protonated methanol or from HCl, whichever you want to use. And then you have an activated carboxylic acid here, and then this guy here attacks into that to this carbonyl. And again, the same old stuff. Tetrahedral intermediate. This guy here then protonates. This guy here pulls off a proton from this intermediate right here. All right, the same as before. Right there, right. And then this guy here then swings on down, kicks off that water. And then you're going here. Then you lose this water here as a leaving group. Then you have this protonated ester right here, which then again gets reprotonated, gets deprotonated by another mole of methanol, which again then goes back to the original thing here, and then starts the process all over again. But the real write-up for this is your carboxylic acid plus your HCl and whatever alcohol you want to use goes to whatever ester you want to make. Okay. So under acidic conditions, just like we talked about before, under acidic conditions, minus charges in a synthesis are avoided if possible. Okay. And so that's what we want to do. Okay. What else here? Okay, so preparation of esters here. Okay, again, like before, if we take your acid chloride here, esters can also be prepared by treating acid chloride with an alcohol. Right, see section 12.8. We already talked about this. All right, we talked about this, and using your alcohol and your pyridine. And pyridine is again to absorb the HCl that you generate because you want to. Not muck with the nucleophilicity of this alcohol. Okay, so you want to do that. Still there. Okay. Esters can undergo hydrolysis in the presence of aqueous hydroxide. It's also called saponification or soap making. All right, and why is it soap making? Why is it soap? What's the deal with that term? Saponification is just an old way. To talking about the process of making soap. If you know anything about the structure of soaps and stuff like that, you know that you have a long chain of alkyl groups here, along with this carboxylate. And so the whole point here is to make a bunch of carboxylates, right? A bunch of carboxylates. And if this is what the active ingredient sort of is in soap, that means that if this is like soap, that means that this long chain here of aliphatic carbons here, absorbs all the oils and all the dirts that are all oil-based on your skin or whatever you're trying to wash off. This absorbs that part because again, like dissolves like, right? And this will dissolve the oil parts of the dirt. They'll get caught up in here, and then you turn your faucet on or your shower towards you, and the water. Right, the water here gets to cling on, sodium plus here, gets to cling on to this carboxylate side here, and then wash everything down the drain. Okay, so this guy here is not attacked by the water. This guy here is, and when you have water kind of raining down, partly partly cloudy, rain showers here. Okay. Once the water comes on down here, it grabs onto this carboxylate and drags everything down the drain. I don't know why I'm really getting into that thing. Anyway, so that's how it happens. Okay, so this again absorbs all the filth and disgusting things from your bodies, like your dep gel and your God knows whatever you're putting on yourself, and then you come home and you rinse off all the sin with water, and this guy here grabs onto that and sucks everything down the drain. Okay, so there's that. All right, and again, so saponification means, saponification here, as again, soap making, it starts normally from a triglyceride. Triglyceride just means this guy here. Let's say triglycerides. It's from a more the sugar type of nomenclature of these alcohol species. And so if you have a triglyceride that is is esterified here, you take 3 moles of your base of your NaOH or your KOH, and you saponify all these positions right here. Okay, to make 3 moles of that and your glycol back there. Okay, all right. And like we talked about before, how do you make these things here? Again, you take your ester, you treat it with a base. It swings on up. You know, the pair of electrons swing on up, and then swings on back down, kicks off the OR minus, and the OR minus grabs this proton right here, forming your carboxylate salt here. Again, whatever the counter ion is here, that's what would be your counter ion there. So like sodium or potassium, and just to change it up, I'll just say it's potassium here, for example. Okay. So again, this is extremely repetitive to talk about, but again, you know, we've seen this before. We've totally seen this before. So base comes in, attacks there, kicks on up, kicks on down, and then from there, that's the rest of the mechanism. Just like everything else, right? Just like every other strong nucleophile that attacks into some sort of a carbonyl group, right? Again, it's all the same nucleophilic acyl transfer type of reactions. Okay, so nothing crazy there. Ester hydrolysis can also be catalyzed under acidic conditions. Also, okay, the carbonyl of an ester is protonated here, and then the water acts as a nucleophile, attacking the carbonyl carbon. Draw out the complete mechanism there, and show how the regeneration of HCl makes this thing catalytic. Okay, and so we'll go over that really quickly. It's again pretty repetitive, but so this is the acid catalyzed ester hydrolysis. So we talked about the base catalyzed, which is very popular, probably the most popular way to catalyze. The most popular way to hydrolyze an ester. Okay, so there's this guy here. Turn this towards me. Maybe it's a little bit better that way. Is it going to be that way? Let's see. No, it's worse somehow. How is this happening? Make it straight. Is that better? That's a little bit better. All right. There's that. R here. Oh, I don't want to use R groups. I'm not going to use R groups. I'm sorry. I'm for some reason I'm all about the OCD this morning. All right. Oh, man, river. How about that? All right. H plus there and water. This guy here protonates. Like that. There's that. Okay, and then from there we can then drag in our water to have it do its dirty work, but it's a water. How could it be dirty? Well, it could be dirty water, right? Like that song by is it the Rolling Stones? No, I don't know what it. I don't think. Love That Dirty Water. That's a Boston thing. All right. OH. There's there. Don't want to forget this. Am I forgetting anything? So this is the bond from that. There's that, and there's this. I think we're good so far, right? I think we're good. All right. And from here, what I would do, I would just again proton transfer. I'm going crooked again for some reason. I have no idea. Oh, whatever. Okay. OH there. Protonate there. There's that. Okay. You get me? OH here. This guy here obviously is this guy right here, right? So I'll just put the proton right there. There's that guy here, plus, and I've lost CH3OH. All right, and we're not quite done here. And then we have water again coming in here, and water or methanol, whichever you want to do. It's all in the same bathtub, so it doesn't matter, right? So H2O. There's just a whole lot more water in here, so that's why we just sort of go with we try and go with whatever the most populous thing is, unless it's wildly different in terms of pKa. So we try and go with like water because there's a lot more of it around. All right, plot that proton right here, swings on back there like so. OH right there, plus H3O plus, which is also H plus. It's becoming more insane, and I don't know why this is. Okay. Keep it together. Keep it. I'm doing fine. I'm doing. Don't. Okay. All right. There's that. All right. H plus plus H2O. Okay. And then that's why you can show that this is a catalytic cycle here, because you generate more H plus and H2O, and there's that right there. And then you go from here to here as you hydrolyze it using acid. An acid catalyzed procedure. Okay, so now you know two ways. You can do the base catalyzed saponification, or you can do the acid catalyzed hydrolysis. But notice, it's not called acid catalyzed saponification. It's only base catalyzed, because it's the metal carboxylate that is the part that makes it a saponification. This guy here, there's no metal counter ion with this carboxylic acid. This is an acid. It's not a carboxylate. Fundamentally different. Looks the same because of the carbonyl, because of the carboxylate here, but it's not the same because of the carbonyl here, but it's not the same in terms of reactivity. Okay, so please know that. Esters can undergo aminolysis. This synthetic utility is limited because the process is slow and because there are more efficient ways to synthesize amides. How would you synthesize an amide? Would you use an ester if you had to? Would you use an ester? Hell no, right? What would you use? You wouldn't use ester. You would use what, an acid chloride, even an acid anhydride. Both totally fine, and use two equivalents of that. But this guy here is slow. Why? Not a great leaving group. Not a wonderful leaving group. Okay, so not really wonderful. So however you want to think about it, you can do it this way, but be prepared to use copious heat here, and not the best way. I've done it because I've had to, and it works, but it's not very good yielding. And again, if you're using a lot of heat, you have to worry about the heat affecting the other, the structure of your R group. So you don't want to do that. All right, be very careful there. Okay. Esters can be reduced using reagents such as LAH, as we know. Two equivalents of reducing agent are required to alcohols are produced through a reasonable mechanism. Okay, we've talked about this. We've talked about this before, right? We've talked about this. There's nothing that's too out of control about this, right? It's the same thing. It's the same thing as looking at Grignard reaction. Okay. Again, I know it's very repetitive. I'm sorry. I'm sorry for saying repetitive. I'm sorry. Eating that is repetitive, but it just is. I just want to point this out to you. Sort of already seen this before. So here's your stuff. Your wicked ester. Sorry about that. So anyway, here's your ester, and hydrogen here. Kicks on down, methoxide, another mole. Hydrogen comes on in. Kicks this guy up here, now here, just waiting around to be quenched. Again, using an LAH, this is going to be stabilized by some aluminum salt, whatever the salt is here. All right, so that will be just sort of waiting around. Right? This will be attached to aluminum. Okay, and then from there, that's when you end up quenching it with your water. Okay, with your water. Again, if you're doing this in real life, don't use water. I have a better way for it. Use the Feezer and Feezer prep. All right, and just email me or come and see me, and I can give you that prep. It's really awesome. It works out so well. All right, but like before, you know how we use that weird triterpetoxy thing to go from an acid chloride to an aldehyde? We can do the same thing with an ester and diba or dibal, depending on whatever book you're using or who you're talking to. But diba or dibal is diisobutyl aluminum hydride. So diisobutyl aluminum hydride is diba, or dibal is diisobutyl aluminum, and then we stop with the hydride. But so diba or dibal, whichever you want to say. For some reason we just say dibal, but either way I'll know what you're talking about if you say diba or dibal. Okay. Why is this only going to deliver one equivalent of one hydride equivalent? Why is that? Because it only has one hydride to give, and the intermediate that it makes is going to be stabilized. So just like before, do I give a mechanism here? I sort of do. Right? No. This is a Grignard. Back to Grignards. Remember, so after this guy here attacks, after this guy here attacks, click. Swing up by so. After we do this, we make this guy here O aluminum. There's your that. There's your this. And there's your OME. There's your hydride. All right. So there's that. And this is going to hang out. This is going to hang out until you throw in some water. So this is after the first step. This is after the first step. You never have this, you never have dibal in water, okay? And then your second step, then you treat this guy here with water, H2O, right? And the water will come in, attack this aluminum. Bing. There's that, and then there is your wicked ester. Okay, so that works out for you. All right, so you can use the lithium triterbutoxy thing for your acid chlorides, or you can use dibal for your esters. By the way, dibal also works with acid chlorides. Also works. I've done that. Works out totally fine. Okay, again, keep it a little cool. Maybe 0. I think 0 was what I did it before. I think 0 is good. 0 or like -10. But coldish if possible. But dibal with esters, room temperature. Dibal with acid chlorides, yeah, keep it a little bit cooler. It gets a little bit hot with that. But again, dibal is a great, is a great way to control the addition of hydride to your carbonyl species with very good leaving groups. Okay, esters, as you know, can react with Grignards. We've done a ton of that, so don't worry about don't worry about it. But again, please refresh. All right. Attacking in, blah, blah, blah. Won't even go over it. We already know it. We already know this, right? We've already been over it, okay? Give reagents necessary for the conversions below, all right? This immediately looks like something out of hell, but it's not too bad, right? It's not too bad, as you know, if you look at it, all right? If you go from here to here versus here to here, there's two different things that are sort of at play, all right? But one thing I want to show you, look at this. Look at this group right here, this seemingly random stereocenter. It is random, sort of, but what it is, it's also a big help to you because you can sort of get your bearings from it, right? Look at that. So go from here to here. What do you notice about the carbon? So the carbon count from here to here is different than it's from here to here. So it's two different preps to go from there, or there to there. So what do you think happens from here to here? Okay, what new things do you see there? Right? What new things do you see? Right? What I see is I see some new methyls right there. Right? And I also see new methyls right here. So what must have happened? What must have happened? You must have had some sort of Grignard or some sort of organometallic attack from here to here. Now, did you use the Gilman reagent? Did the Gilman reagent happen? No, the Gilman reagent is not really that effective on esters as much as you'd like it to be. It does work in some respects, but not as good as if you use acid chlorides. But we don't have those. We have an ester here, and then we have a lactone here. Okay, so lactone is a cyclic ester, and here's an ester right here. All right, so I would think about using methyl magnesium bromide, or methyl Grignard 1 followed by water 2. All right. How do I know that? How do we know what happens? Well, because you have 4 more methyls in this answer than you do in this starting material. Okay. Grignard attacks here twice, right? The first time it kicks this guy out here. The second time it adds making the tertiary alcohol. This guy here attacks this guy here in twice. All right. First off, kicking off the rest of this beast here, and then the second time adding in to make its tertiary alcohol, followed by water. You make a bunch of magnesium bromide salt, then you hit it all with water, and then you get this entire mess right there. Okay. From here to here, what do? Looks like you must have done something. You see, again, you still see no carbonyls, but this guy here. If you treat this guy here with something, this guy here looks like this guy here. It's separated by this ester. Whenever you see esters, look at breaking the ester and see what you can make if you have this kind of a problem. There's no esters in here, so they must have been either reduced or they must have been reduced in some fashion, right? They must have been, we must have added some carbons to it or some hydrides to it or something to it, right? So if we think you add some methyls or some alkyls to this using some Grignard, we see no evidence of that because the carbon count is the same from here to here. But what might we have added? We might have added a lot of hydrides, all right? And what hydride source attacks esters all the time, right? Right? Do we know two reagents? Two reagents that do a lot of carbonyl reductions? C C-E-A-K. All right, C-E-A-K. All right. So AK, aldehydes and ketones, are sodium borohydride, right? But all of them are LAH. So these are all esters, which just falls right here. So this must have been the LAH that reacted here. So LAH. Do out that mechanism as well. Pretty simple, and they're both very, very, very similar. All right. So convince yourself of that. All right. Amide can be hydrolyzed with H3O, but the process is slow and requires high temperature. Thank goodness it requires lots of heat and slow, because we're made of a bunch of peptides, and all peptides are amide bonds, like long alkyl chains with lots of amides on there, right? And thank goodness that we need heat and whatever to break those down, because we would just dissolve. We would be like one of those vampires in True Blood, if you're a True Blood fan. Wow, that's just dated. We know it's so funny because True Blood was even back here in the olden times, so I'm recording it back in the past. So again, we don't know what time it is, what year this is, but it might be, well, vampires are forever, right? So I might be a vampire. I could be up to 1,000 years old if I was a vampire. I'm just going to stop talking about this. All right, I've beat this dead horse. All right. So this requires lots of heat and lots of acid, even some base too. Again, but lots of energy. All right, so this does not happen. So please don't try to hydrolyze any amide with any heat and any acid. It just doesn't really go for it. Okay, should the equilibrium favor the reactants or the products? Well, if you're looking at entropically speaking, this guy here is 2 particles here to 2 particles here. So entropically, using a lot of hand wavy techniques here, is almost a wash. But here you have to break into some really cool, very stabilizing resonance to be able to break this guy here, right? To be able to generate this guy here. So you don't want, so that's also very hard to do. Also, okay. Also, you don't have the strongest nucleophile, even no matter how much heat you have. Water is only so good of a nucleophile, even with some acid, even protonating this. Okay. When you protonate this guy here, you don't necessarily break resonance of here, right? Like you do in some other ketones, where you have, it being you can influence some resonance in one direction if you protonate it. When you have an amide and you protonate an amide, you don't influence its resonance very, very much. So that's something. All right. So you want to make sure that you you never try to implicate this in a sort of synthesis. Okay, the ammonium ion here comes from the balancing of the equation of using the acidic proton from here, along with the acidic proton from here along with the rest of the NH from your thing that you've cleaved as well. Okay, again, both are very slow. The acid and the base catalyst. So we almost never use it in any implication, okay? LEH can reduce an amide to an amine, which is pretty, again, also pretty slow. Not something I would do, obviously, but it does work. It's synthetically sort of useful if you control it. If you don't control it and you get some water in there, it's going to hydrolyze this puppy. So you want to be very, very, very careful with this. Again, I speak from experience here, folks. So the mechanism is quite different from others that we've seen in this chapter. Okay, so when hydride attacks here, it attacks directly into here. Okay, and let's just go into this mechanism. So hydride, LEH, the hydride attacks right into here and gives you the species here. Then you make this aluminum hydride thing here. All right. So as soon as you form that, then this guy here swings on down and kicks off this aluminum oxide species. All right. And forming the iminium species here. Okay, the iminium is then reduced with a second equivalent of hydride. So you take the aminium, and this is again reduced with a second equivalent here. This will attack right in there, giving you your primary amine. All right, which is pretty cool. But again, you've never really seen this as a leaving group, sort of. You sort of have you've never seen this exact leaving group with the aluminum. All right, so I was gonna say you had some leaving group stuff with. With other LH reactions, but I've never shown you this one, so don't worry about it. So this guy here helps to form the aminium right there, and a hydride comes in to attack this carbon right there, kicking this guy up here, quenching this N plus, and giving you your primary amine. Okay, so it's a little bit different, but again, still the same concept of attacking an electrophilic carbonyl. Okay. All right. When a primary, let me take some more coffee here. Jesus, I've just been blathering on. Why don't you guys talk? Tell me what's going on with you guys. How you doing? How's everything going? All right. Talk amongst yourselves. Oh, good heavens. All right. When a primary or a secondary alkyl halide is treated with a cyanide, the cyanide acts as a nucleophile, and SN2 reaction occurs. We've seen this before, right? We've seen this alkyl halide in some respect, a bromide or chloride, gets treated with this cyanide ion to give you this cyano compound here, all right? And from here, we know that we can treat this guy here with acid or base and make the carboxylic acid or the carboxylate respectively, whichever way we want to do it, okay? Which is pretty awesome. All right, so that's one cool way to prep a nitriel. Okay, that's one cool way, just again, SN2. But another way, right? Another way is by treating, and this is going to be crazy, right? Nitrous compounds can be made by dehydrating. Dehydrating? What? Dehydrating OH2. Woohoo! Dehydrating an amide using a variety of reagents, including thionyl chloride. Thionyl chloride helps to dehydrate an amide to a nitriel, okay? Making SO2, 2 moles of HCl, and the alkyl cyanide. You know? Okay, so how do you want to do this? Okay, let's take this guy here. Let's take your regular primary amide here, and this guy here will attack the oxygen. Will attack this sulfur right here. Now, notice how similar this guy here looks to like slide number 39 or whatever we start, or 29 or 30 or 31 that we talked about before. All right, this looks very similar. You make this guy here, just like you'd make it if this guy here was an alcohol. This guy here would attack in right there. All right, very similar to the beginning of this lecture. All right, and again, very similar to the alcohol attack of that guy right there. All right, so this guy here attacks this, kicks off the chlorine that we had talked about before. Very similar mechanism there. But now what do? We take the base and we pull off. And what base might you use here? What base might you use? Oh hell, you'd use pyridine, triethylamine, something that's non-nucleophilic. Has to be non-nucleophilic. Why? If it's a good nucleophile, it will attack in that thionyl chloride. So something strong but non-nucleophilic. Okay. The base pulls off this proton over here. All right. Goes back down there, making this going from a positive charge to a neutral charge right here. Then another mole of base pulls off that proton right there. This swings on out and kicks off this guy here, making SO2. You know what's so weird about your book? Look at what they do here. They make the SO2 and the chlorine in one step here, but when we talked about making the acid chloride from the carboxylic acid, it's like, oh no, we do this and make this other weird thing, and then we do this. It's the same stupid mechanism. I have no idea why. I don't know. If I could answer these questions as to why your book makes these choices, I have no idea. By the way, fans of Cylon or fans of the Cylon book, I'm sorry. It's a good book overall, but I guess I'm just being picky. All right, it's how I am. All right. So this pulls up this proton right here, makes the neutral imine base here. Pull off another proton right here. This swings on down here, kicks off. Breaks the carbon-oxygen bond right here and kicks off the chlorine right there, giving you this cyanide. Please do this mechanism over and over and over until it is second nature to you. Okay, it's not hard. It's a lot to keep track of. So do the amide to nitrile mechanism and do the carboxylic acid to the acid chloride mechanism. It will serve you well, I promise you. Aqueous strong acid can be used to hydrolyze the nitriel. We went over this in lecture, so I won't bore you with it again. Okay. Pretty straightforward stuff. You take your nitriel, and you hit it with your acid, and you make your amide right there. Okay. But you take more acid here, and then you go right to this guy here. Now, I don't like to stop at this amide, because once you stop at the amide, it's hard to stop. It's hard to just say, and then it continues on forward. I continue. I don't ever stop here. I make sure that things are in a way that that you never come to this, because once you come to this again, like we saw a few slides ago, this is very hard. This from here to here is very hard to do. All right, so make sure that when you see the mechanism, you don't stop here ever. You stop at this other one where you have a partially reduced, partially partially reduced carbon species there, which then goes on and kicks off the NH2. All right, so never stop here. Never stop here. Okay, refer back to my mechanisms that I gave you in class. All right. All right, base hydrolysis of the nitrial can also be achieved too. Again, we've talked about this in class as well, so please refer back to your notes there as well. Okay, but again, just to refresh your memory, it's the OH. Okay, the OH there attacks into that carbon right there, kicks on out. Blah, 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 R, carbon there, nitrogen there, there's your OH right there, your nitrogen there grabs this proton right there from hydroxide right there, all right, and then again continue on with this until you keep on protonating this nitrogen, keep on removing the protons from here to give you your carboxylate, which then gets reprotonated. Okay, we went over this in class, so just refer back to your old notes there. Okay, which group? Okay, we talked about all that. Now here's something cool. Here's something very cool. Okay, this is a variation on our last mechanism. Okay. If you take a Grignard and react it with, and you treat it with a nitrile here, okay, you get to make this guy here. But you can, if you use the right, if you use the right alkyl group and some acid water, you can make a ketone right there. So this is another way to make an asymmetric ketone species from a Grignard. Okay, so it's actually sort of cool stuff. All right. So after this step here, so we'll start from, so after you make this guy right here, we'll continue on with this mechanism. All right, this guy here gets, and again, so the first step is going to be your Grignard. That's going to be your first step. And your second step is going to be, your second step is going to be your H3O plus. All right. So now this is your first step. Then your second step, your H3O plus, is the following step here. So here is your imide, your imidate, I believe it's called, gets protonated from acid water, and then protonated one more time to make it activated. Your water comes on in here, kicks on that guy right up there like so. Your water pulls off that proton right there. Okay, make sure in this guy here, make sure carbonylamine. We talked about this intermediate before. Okay, carbonyl from your alcohol amine, which then gets reprotonated again, okay, right there, giving you this NH3 right here, and this pair of electrons will swing on down between the carbon and the oxygen and the carbon, kicking off this NH3 right here, giving you this ketone, right? And again, if R prime and R are different, and they are going to be because I just named it, name it differently, R prime here, 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 all right, and then we flip it around. It's still going to be the same R prime because you're just pointing upside down. All right, R prime there, and then there you are. Okay. So pretty cool, huh? This guy here swings on down, kicks off the NH3, gives you the ketone right there, which then gets deprotonated with this water, and giving you this ketone right here. So pretty awesome, huh? Yeah, please know that mechanism as well. So notice this is like it's not. Keep your wits about you. If you try to memorize this mechanism, you will be completely hosed. Try just to know what your goal is. Know what your goal is going from here, going from R, C triple bond N to here. Your goal is R and R prime. And what do? The first one is R prime MgCl. Your second step here is H3O plus. Don't forget your goal, and keep this in mind, all right? So when I ask you for the mechanism of this from here to here, make sure you draw the answer out first, because after a few of these things, you're going to know what the answer is based on this reaction setup. So make sure you always put the answer down first, and then go back and then draw the mechanism towards it. And whenever you start to lose track of what you're doing, right, make sure you look to your answer and you're like, okay, I need to make sure I get to this where the carbon oxygen has a double bond, and I need to make this a better leaving group, and it's an acidic medium, so I'm going to keep on protonating this until it's a good leaving group, and then have it leave. All right, so just make sure that happens. Okay, so make sure that you don't lose sight of what you're doing. Okay. Similar to how carboxylic acids can be converted to alcohols using LAH, from that scene there, nitriles can be converted to amines as well. And we learned this in, again, in the prior chapters as well. Okay, so we know how to go to make this into a ketone, into a carboxylic acid, and now we know, and again using LEH and water, we now know that we can reduce all these guys here down here, again using hydride as a nucleophilic source, right? Over and over and over again until we get to this guy here. All right, so cool stuff, eh? Cool stuff, I promise. Okay, synthetic strategies. When designing a synthesis, there are two general considerations that we make. Is there a change in the carbon skeleton? And is there a change in the functional group here? We have learned many new functional group transformations in this chapter. Did we make a change to the carbon skeleton? No, we didn't cleave anything really, right? We learned that in with Baeyer-Villiger. That was the last thing that we learned how to cleave, right? But we changed a lot of functional groups. We changed a lot of esters and carboxylic acids and acid chlorides and amides back and forth to each other. Okay, and so we learned a lot about that, and then we've learned a little bit more to appreciate the acetonitrile, right? The cyano group as a really multifunctional functional group to be able to add in many things that we need to be able to change it into. Can we change it? Do we need to use that to make a ketone or an aldehyde? We can do that, or carboxylic acid or an amide. We can do all these things now, which is pretty awesome. Okay, so make sure that we know all the functionalities there. Okay, now this is sort of a summary-ish of our. Is there anything else after this? Yeah, one more. All right. So again, going back to the carboxylic acid, please know the first generation transformations, which is the acid chlorides, anhydrides, esters, amides, and nitriles, but also each of their interconversions, and then going back from here to aldehydes or alcohols or amines, and try and go from here to there, or from this. Oh, look at this. Go from this alcohol to this guy right here. Can you do it? Sure. There's absolutely all kinds of paths that go that way. All right. So again, try these things. Try these like different ways to do it. Now, we don't have a lot more to go on this in this semester, so I know that time is growing nigh. But just again, this is the thing to really focus on. This is one of the most important things about organic chemistry. These type of transformations. All right. So take your time here. Give necessary reagents for the conversions below. Multiple steps will be necessary. Do you know how to go from a nitrile to an aldehyde directly? Is there anything from and to that you know from here that goes to an aldehyde directly? Nothing directly, right? Because if you knew that, this would be highlighted here, right? Do you know anything directly? Not particularly. So I wouldn't worry your pretty little heads about that. All right, but how do you go from here to here? Well, obviously you've oxidized this a little bit with to make an oxygen there. All right, and that guy here. So do you know how to go from an acetonitrile to an amine? Sure, but that's not what that is. You know how to go to acetonitrile to a carboxylic acid? Sure, you do. Can you go from a carboxylic acid to an aldehyde? Oh, hell, you do. You know a few ways. How? All right, so carboxylic acid to an aldehyde. Well, learning our typical, learning our brand new knowledge. We can think about this. We can change this to the carboxylic acid using some acid, right? And then from there we make the thionyl chloride. We treat it with thionyl chloride, making the acid chloride. Then treat that with dibal or lithium triterbutoxy aluminum hydride. That'll give you that directly, or carboxylic acid reduce using LEH all the way down to the alcohol, then PCC all the way, then PCC half the way up to the aldehyde. So we know a bunch of stuff there. Okay. So, and there's also, I'm sure, many more Baroque ways to get to it as well. If you want to add another carbon to it and do an ozonolysis, I wouldn't recommend that. That just seems to be wasteful. But a bunch of ways to get to that. Okay, so please, practice that kind of thing. There are two categories of bond-forming reactions here. One in which the carbon-carbon bond-forming reactions where the functional group remains in the same location. So this guy here is going to be still staying there. This guy here is still staying there. Okay. And this guy here, the carbon of this is still the carbon of this guy here. But here's where you add on a carbon, where you involves a change of the location of the functional group here. We add the cyano, and the cyano is your source of carbon here, because right here you went from a 2-carbon entity to a 3-carbon entity, right? And here is you add on that carbon right there. And if you're doing this Grignard where you're throwing on your CO2, you're adding on a 3rd carbon right here as well. Okay, so you're not transposing it. That's a wrong word to use, but you're adding, you're changing the location of the main part of the functional group here. I also would probably throw in this other thing. I'd probably even throw in maybe the reactivity of using the epoxide. If you were to make this, the Grignard, Mg0, the M to the 0, and ether, and then have this guy here be the second step, and then you'd make the 1, 2, 3, 4, and then you'd move this 2 carbons over and make the alcohol on of course the 3rd step would have to be water, right? Of course. And then you'd move this 2 carbons over versus 1 carbon over. Okay, so a bunch of different ways to do these things. So isn't that sort of awesome, right? You're learning a lot of new ways to be able to transpose carbons, huh? Here, okay. So when forming new carbon-carbon when forming new carbon-carbon bonds, it's critical to install functional groups in the proper location. Give reagents for the conversion below. More than one step will be necessary. Okay, so you have this guy here, which is this guy here, and then you want to make this guy here. Okay, all right. Well, how do we do that? Do we know how to do it? I think we do. We're only adding in 1 carbon, and that 1 carbon is part of the carboxylic acid. So your favorite, so your new favorite transformation, right? Everyone loves this for some reason. I know why. It's actually a very cool thing. You want to make a carboxylic acid, sure, and make this a Grignard, and then bubble in CO2, right? Do this guy right here. It's a good way to add a carbon that is part of a carboxylic acid moiety. All right. So cool stuff, right? So this guy, so the first step here, magnesium in diethyl ether. Second step is CO2, bubble in that, and then the 3rd step would be, of course, protonation to give you the carboxylic acid. Okay, so I want to thank you for your time and attention here. Cool stuff. We're running at about an hour and 37 minutes at this point. Again, roughly the same time as a lecture. But thanks for letting us finish this lecture this way. There's a lot more to get to before the end of the semester, which is coming up very, very, very quickly. So study hard, and don't get overwhelmed. Breathe. Don't forget to breathe. Have a burrito every once in a while, and study hard. I just said that, but we can be repetitive. Okay, so everybody, see you soon, and be safe, and save your beef. That was just weird. All right, ta-ta.